All right. This is the this part of the physiology is devoted to the hemodynamic laws, and at these curves you will see the different parameters which are described the different stages of the blood flow. You see, this is the aorta, the vascular bed, the different blood vessels, aorta, arteries, arterioles, capillaries, venules, veins, and large veins, and vena cava. This is some parameters, 1, 2, 3, 4, 5, 6, the main parameters. First of all, this is the blood flow, the volumetric blood flow. What is this? This is the stroke volume. It is equal 65 milliliters. Stroke volume, this is the volume which pumps out from the left ventricle into the aorta. And we multiply to the heartbeat rate, 75 heart beats per 1 minute. Approximately it is equal 5 liters per minute. This is the it is known cardiac output, or the other words, this is the blood flow, and we mark this blood flow with the letter F, flow. It doesn't change, but you should understand that in each vessel, in each capillary, or in each artery, the flow is the minimum. This is the blood flow in all capillaries, in all arterioles, in all venules, in all veins. It doesn't change because the blood pumps out of the blood, and then it is distributed in the small blood vessels, but in common the blood flow in all vessels with one diameter is the same how the amount of the blood flow through the heart and through the aorta. This is the other parameter. This is the common cross section, S common cross section. What is this? This is the figure P 3.15, and it is multiplied by the radius in square, but not one radius of the vessel. This is the summation of all radius of all vessels. This is the radius of the vessels of all capillaries, all arterioles, all venules, and you see this is the radius. The diameter of the aorta is approximately 1.5 centimeter. This is the radius, the half of the diameter. We multiply by 3.15, and approximately this common cross section is equal 5 centimeters in square. In the capillaries, the common cross section is maximum, approximately 3,500 centimeters in square. And the common cross section decreases in the veins, and the common cross section approximately is equal 7 centimeters per second, because the diameter of the vena cava is equal approximately 3 centimeters. This is the very important parameter. This is the linear velocity. This is the volumetric blood flow. It doesn't change in all blood vessels, but the linear velocity decreases. the maximum linear velocity happens at the beginning of the aorta. The rate of the linear velocity 50 centimeters per second. Then it is decreases, and in the capillaries it decreases less than 1 millimeter, a half millimeter per 1 second. And then the linear velocity start to increase again in the veins, and in the large veins and in the vena cava, the maximum linear velocity is equal 10 centimeters per second. This is the 50 centimeters. This is the 10 centimeters per second, because the diameter in the veins is larger than the diameter of the aorta. This is the special formula which can help us to investigate this linear velocity. Linear velocity from the V velocity. It is the blood flow F divided by common cross section S. F divided by P multiplied by summation of the R in square. And this dependence describes only the maximum linear velocity. After the pumping out of the blood from the heart, the linear velocity decreases during the diastole and goes to the minimum approximately near to the zero. Then the next pumping out of the blood from the heart, and the linear velocity increases again. That's why we have the vibration, the oscillation of the linear velocity in the arteries. Then we have the same without vibration of this velocity in the small blood vessels, in the capillaries, in the arterioles, and in the venules and the small veins. The next parameter, this is the diameter. This is the 2.5 centimeters, 2.5 centimeters, and this is the 3 centimeters. The radius is a half of this centimeters, of this diameter. And this is the minimum diameter. This is diameter of one vessel, of one aorta and one capillary. This is the common cross section. This is the square of all capillaries. But this is the diameter of only one capillary. It is equal 8 micron. What is the micron? The 1 micron is 1,000 part from the millimeter. And I show to you, this is the cross section of the capillary. This is diameter 8 micron. The diameter of the erythrocytes, you should know from the histology course, 7 microns. That's why the erythrocytes flows in the capillaries one by one, because the diameter of the capillaries can't be less than 8 micron. Because it will be less, the erythrocytes can't flow through the capillaries. But the erythrocytes, red blood cells, they transport the oxygen to the metabolic processes in all parts of the body. This is the next very important parameter. This is the vascular resistance. The vascular resistance, R from the word resistance, the first letter. It is depends on the formula of the Poiseuille. The Poiseuille law. This is the Poiseuille law. This is the French scientist who described this dependence. 8. This is the coefficient. This is the nu. This is the viscosity. The viscosity of the blood is equal 5. The 5 time is much than the viscosity of the distillate water. It depends on the proteins, first of all, the proteins in the plasma. And viscosity depends with the red blood cells, leukocytes, and thrombocytes. It is equal 5. And under normal condition in the healthy body, it doesn't change. It may be changed at the lack of water in the body or increase of water in the body, but at the healthy body, this is the steady of this parameter. This is the length, L, this is the length of the vessels, the length of the capillaries, the length of the arterioles, the length of the aorta, and so on. This is the P, the figure P, 3.15 multiplied by R. This is the R radius. This in this formula, this is the summation of all radius of the vessels, of all capillaries, all veins. But this is the radius of a vessel, of one vessel in the fourth, in the 4 power. That's why this is the coefficient, this is the coefficient, this is coefficient, and the resistance depends only really on the 2 parameters. The length, the more length of the vessel, the more vascular resistance. The more radius, the less vascular resistance, or the less radius in the capillaries. The capillaries have the minimum radius, the maximum vascular resistance. At this curve, I present to you the vascular resistance in percent in different parts of the vascular bed. In the arteries, only 10% of the vascular resistance. 50% in the precapillary sphincters, at the small arteries and in the arterioles. A little bit less in the capillaries. No maximum. You see the maximum of the common cross section at the capillaries, the minimum linear velocity at the capillaries, the minimum diameter at the capillaries, but the vascular resistance is maximum before the capillaries, not at the capillaries, and the 5% in the all veins. If we multiply these values, we will have 100%. What is the vascular resistance? The vascular resistance, this is the force which that prevent to blood flow. The heart works against this vascular resistance. And what is the nature of this vascular resistance? The vascular resistance, this is the friction between the blood and vessels wall. The inner surface of the all vessels wall consists of the endothelial cells, and in the inner surface of the endothelial cells, the glycocalcium, you know this from the histology course, the glycocalcium is located. What is this glycocalcium? This is the hydrochloric molecules, and the proteins and the blood cells make the friction with the glycocalcium in the different parts. And why this is the maximum vascular resistance, the maximum friction, not in the capillaries, but before the capillaries, because the minimum radius in the capillaries, but the length of the capillaries is very small. This is the more wiser capillaries. This is the 8 microns. This is the 20 microns. But the length is more in the arterioles and small arteries than in the capillaries. That's why the maximum vascular resistance happens before the capillaries. The second stage, this is the resistance in the capillaries, and minimum resistance in the arterioles and in the veins. In the surgery, the surgeons at the wound, they change some blood vessels to the plastic vessels. The plastic vessels has no vascular resistance, have no resistance. The pressure doesn't decrease at the during these plastic vessels. At the beginning and the end of these plastic vessels after the operation will be the same blood pressure, but the natural our blood vessels has the glycocalcium and the friction, and it is known in the physiology vascular resistance. This is the last, the most important curve. This is the blood pressure. This is the systolic blood pressure, 120 millimeters of mercury, and diastolic blood pressure, 80 millimeters of mercury at rest at the healthy body. The blood pumps out of the heart, and first of all, the blood pressure increases, then it decreases. Then the new cardiac cycle and the blood pressure increases again. But little by little, according to the vascular resistance, blood pressure starts to decrease. And maximum decrease happens not in the capillaries. It happens before the capillaries, because the maximum resistance happens in the small arteries and in the arterioles. The dependence is this. This is the change of the pressure. This is not the absolute value of the pressure. This is the change of the pressure. What is this change? This is at the beginning of the arterioles, for example, this is the P1, and at the end of the arterioles, P2. P1 minus P2, this is the difference of the pressure. And this difference of the pressure is have the right dependence on the blood flow, this F, and the resistance. Blood flow in the all blood vessels doesn't change, 5 liters per minute. That's why the blood pressure, the change of the blood pressure, depends really only to the vascular resistance. The more resistance, the more change, the more decrease of the blood pressure. A little bit in the capillaries, and then the blood pressure decreases little by little in the veins to the zero. One complicated question arises: how the linear velocity depends on the blood pressure, or how the blood pressure correlates with the linear velocity. You see that in the arteries, the linear velocity is decreased, and it has the minimum in the capillaries. The blood pressure decreases as well. But in the veins, the linear velocity starts to increase again. But the blood pressure goes down little by little, step by step, It doesn't increase. Why? What is the correlation between these two parameters? This is the same correlation, the decrease, but in the veins, there are no correlation. Why it happens? It happens because they depend on the other parameters. The linear velocity depends on the blood flow and the common cross-section. It is inversely proportional to the common cross-section. The common cross-section decreases in the veins, it maximum in the capillaries, and the blood linear velocity increases. But the blood pressure doesn't depend on the common cross-section. It depends only on the vascular resistance. The vascular resistance every time decreases the blood pressure. That's why the right answer, what is the correlation between the linear velocity and the blood pressure? There are no correlation. This is the two different parameters of on the blood flow. What is the interrelation? Interrelation through the F. Flow, the same. This is the F. This is the F, this is the F, and this is the F, blood flow, but it doesn't change. It doesn't change. That's why this linear depends only on the common cross-section, and the decrease of the blood pressure correlates with the, inversely correlates with the friction, the vascular resistance. There are the two very important questions which are askable at the exam very often. What principally, without these curves, I hope you will redraw these curves. I will send to you the more precise curves, more clear C curves, and you will redraw in your notebooks. But usually it asks, what is the reason why the blood flows in the arteries? Three reasons. First of all, the pumping out of the blood. This is the heart work, the main reason. Then this is the common cross-section, which increases little by little, and the vascular resistance. It depends of it influences they influence to the linear velocity and to the blood pressure. And what is the reasons of blood return to the heart in the veins from the legs, or from the foot, for example? Why it returns to the heart? The veins includes a lot of the reasons. First of all, this is the small difference of the blood pressure. This is more, this is less, this is the 0, and this is the 20 millimeters of mercury at the end of the capillaries. But the second reason, this is the semilunar valves. In the large veins, they in the space on the veins, the semilunar valves are located, and they prevent the blood flow in the reverse direction. The blood in the veins may flow only to the direction of the heart. Then the next reason, this is the negative interthoracic pressure. When the inspiration happens, when we breathe the air, the volume of the thorax cavity increases. And the pressure in the lungs, in all blood vessels, start to decrease. And the blood flows from the abdominal cavity, from the veins from the abdominal cavity to the veins in the thorax cavity, according to the decrease of the pressure in the thorax cavity. Then the next reason, the at the beginning of the diastole of the atria, of the both atria, the pressure is minimum in the atria, and the blood flows with the atrial pump. It is no atrial pump or the heart pump. It happens to move the blood, to flow the blood in the both atria, in the right and left atria. Then the next reason, this is the muscle pump. When the skeletal muscle contracts in the extremities, in the legs, in the arms, they compresses the veins, and the blood flows in the veins in the direction to the heart. But when the skeletal muscles start to relax, the semilunar valves prevents the abnormal movement, the blood in the reverse direction. And the next reason, this is the pulsation of the nearby arteries. You know from the anatomy course that the arteries goes in the extremities with the two veins. And when the pulsation of the arteries happens, it presses the veins and a little bit help to move the blood to the direction of the heart. Thank you for your presence at our conference, and we